So in the last class, we discussed about the eightfold way and how the eightfold way was successful as compared to the other previous model. Now we will discuss about the Cork model. So the eightfold way was which got more order in elementary particles. Also, it predicted some missing particles that we already discussed in the last class. So it was using that eightfold way method, it was able to predict some of the uh, particles, elementary particles, which were not known at that time. For example, the omega minus. They also, in this eightfold way, they also predicted all the properties associated with those particles which were not discovered at that time. And later on, it was experimentally observed, and that made the eightfold way a successful model. So this eightfold way was able to make some more ordered way or some kind of a classified structure to the elementary particles, and it also predicted the missing particles like omega minus in super multiplets, but it was not able to explain the existence of new particles or new super multiplets, which were also not known at that time. So at that time, in order to explain those new super multiplets, the eightfold way was not enough. It failed to explain the existence of new super multiplets. Also, it couldn't explain the particular mass of those particles. They explained many properties associated with those particles, but when it comes to the mass, it was able to predict somehow for some particles, but it was not able to predict all those particles, new particles, mass accurately. So these are the limitations which were faced by this eightfold way. First one is that it couldn't explain the existence of new super multiplets, and it was also not able to explain the particular mass of those particles. Okay. Then in 1962, Niemann and Heim proposed that the baryons are made up of more fundamental components, but at that time the response was not that much good from the scientific community because it was just a proposal and there were not much evidence associated with that. So this Niemann and Heim proposed this idea that the baryons are made up of much more fundamental small particles, but it was not that much successful. Those proposal was not that much. It didn't got that much response from the scientific society. And in 1964, 2 years later, Gell-Mann and George Zweig proposed the Cork model. The same kind of concept that the baryons are made up of some more fundamental components. This concept were taken from this proposal and Gelman and George Zweig, they proposed the Cork model in 1964. So what is this Cork model? According to this model, all hadrons are composed of three fundamental particles called quarks and their antiparticles. So this is the fundamental point or fundamental postulate of this particular theory, Cork model. So according to this model, all hadrons, considering hadrons only, we are not considering those leptons here. We are considering only hadrons. You check that classification. We are considering those hadrons class. So in that hadrons group, okay, all hadrons are composed of three quarks, three fundamental particles. These fundamental particles are known as quarks. Okay. So all hadrons are composed of three fundamental particles, which are called quarks, and their antiparticles, the antiparticles of those quarks. So then in those hadrons, if you consider mesons, those mesons are having quark anti-quark pair. One quark and next one is anti-quark. So these two particles, pair of these two particles, which forms the mesons. So one will be quark, the other one is anti-quark, and this pair forms meson, those meson group. And if you consider baryons, the other hand, consider from that hadrons, if you consider baryons, these baryons are composed of three quarks. They are having three quarks, not having only two. They are having three quarks, and it can be different. Okay. So here in for the mesons, it is quark anti-quark pair, but in baryons, it will be having three quarks. Okay. Now, if you consider these antibaryons, like baryons, we have antibaryons. For the antibaryons, we have three antiquarks. They are having three antiquarks. So baryons are having three quarks. Antibaryons are having three antiquarks. Now this model explains all the properties of hadrons. Okay. So this model also solved many of mysteries in particle physics. For example, if you consider those Cork model, then we have first we'll consider this UDS. These are up Cork, down Cork, and strange Cork. These are the important one. And then we have top, bottom, charm. That we are not going to discuss here, but they are also there. Then we have color, Cork, all those things. So these are the important one. These are up, down, and range quarks. So this is the Cork table. You can see from here. First one is Q. This is the charge of each quarks, and this one is the baryon number, which is A. Then we have the isospin I, and then we have S. Okay. So yes, strangeness. So this is the strangeness. So here we have Q, which is a charge, with A, which is the baryon number. Then we have isospin. Then we have strangeness. Here we have up quark, down quark, and strange. this is the Cork, okay, and this is that value of the strangeness quantum number. Now, if you consider these three quarks, UDS, we have a charge of 2/3 for U, that is up quark. So this one is up quark. This one is down quark, and this one is strange. Okay. Then here it is charge for up quark we have charge of 2/3. Then for down quark we have charge of -1/3. Then strange we have again charge of -1/3. We have here -1/3. Similarly, baryon number, if you consider the baryon number for up quark, which is 1/3, and for down quark also it is 1/3. For the strange, it's also 1/3. And isospin is 1/2 for up quark. For down quark it is 1/2, and for strange it is 0. And strangeness, if you calculate, strangeness is 0 for up quark, 0 for down quark, -1 for strange quark. Okay, so these are the quantum numbers charge which is associated with those quarks U, D, and S. Now, if you consider their antiparticles, then you have U bar here. Here is U bar, this is D bar, have S bar, and this will form the antiquarks. Okay, so here we have Q, A, and S strangeness, Q, A, and S, which will change to its negative values. This changes to negative. So that is the only difference associated with this anti-quarks, which are U bar, D bar, and S bar. For Q and AS, all these values which we just listed here, they will just change their polarity. That this charge, when you consider here for U bar, that will become -2/3. For example, if you consider this one, so here it will be like, here it will be for U bar, it is -2/3. Then for D bar, it will be 1/3. And for S bar, it will be 1. So those values will be having different sign. That is the only difference that we can expect for these anti-quarks. Only this charge, baryon number, and strangeness, their values will become opposite polarity. If it is negative in quarks, it will become positive in anti-quarks. If it is positive for quarks, it will become negative for anti. Now, if you consider some examples, for example, proton, if you consider proton. So protons are not fundamental, or they are not the elementary particles. Proton consists of 3 quarks because it is a baryon. So which are having U, D quarks. So which consists of 3 quarks inside this proton. They are having different spin, like this. This up quark is having spin up. Then another up quark is there. So all quantum numbers are same, but this spin should be down, so that the Polish exclusion principle should not be violated. Similarly, if you consider neutron, neutron is also having three quarks because it is a baryon. So it is U, D. So here also we have two D, two down quarks, so their spin should be different so that the Polish exclusion principle should be validated. In order to obey those Polish exclusion principle, these two down quarks should have different spins. Okay. But in some cases, we can have those Polish exclusion principle which is violated. For example, if you consider here for omega minus case, we have three strange quarks, three S quarks like this. All of them having spin out, spin up. Okay, because this omega minus is having total of spin 3 by 2. So in order to get their spin 3 by 2, we need 1 by 2 plus 1 by 2 plus 1 by 2. Okay, so for all those spins should be up. In this particular case, the Polish exclusion principle will be violated, but we have some different scenario that we will discuss in the later section of this lecture, how this can be, this Polish exclusion principle violation can be tackled. Okay. So other examples you can see from here, delta plus particle, if you consider another baryon, you have you up and down with the spin in this direction. You can see here. We have here also three up quarks with the up directions. So different. If you consider rho plus, or if you consider K plus, we have only two quarks. This is U. This is S bar. So these are the quarks associated. This is having spin down. This is having spin up. So this is the quark associated with that cavern with the first charge. So I will just show that in this table here. I'll just erase these things. Okay, from this table you can see that different baryons. You can see here for different baryons we have proton UUD is the core combinations, and for neutron we have UDD. In this case, for lambda we have UDS. Okay. Similarly, for P bar, which is antiproton, for antiproton we have all the quarks which are anti-quarks, which is just the anti-particles of these up-down quarks. So U bar, D bar will be the quarks associated with the proton, antiproton. Similarly, N bar, neutron, anti-neutron, we have U bar, D bar, D bar. Similarly, for lambda bar, anti-lambda particles, which we are having U bar, D bar, and S bar. But if you consider the mesons, for the group mesons, for mesons we have only two quarks, and they are having quark anti-quark pair. So pi plus we are having UD bar here. Just right here. Pi plus, if you consider this is meson, pi meson. So for mesons we have quark anti-quark pair. Only two quarks are there. Okay. One is quark and the other one is anti-quark. So they are having two particles or elementary particles which are quark and anti-quark, which their pair. So this pi plus is having UD bar, okay? And if we consider pi minus will be having DU bar. So one quark and another one is anti-quark. So this pair will be there for mesons. And if you consider K plus here, K plus, which is US bar. So one is cork, the other one is anticork. So cork anticork pair forms the mesons class. All those mesons are formed with those cork anticork pair by the Cork model. Now, if you consider the confined quarks, how these quarks are confined in that particles, so you can also see from here how we can represent this. So, for example, in this case, pi minus is pi minus here, so it is nothing but du bar here. So d here and u bar here. So this particle, this whole is the pi minus, and it similarly you can see here lambda. So for lambda we have u, t, s. So we have three quarks that are confined in this volume, this particular area. So that will form this lambda particle, u, t, s. So u, t, s is. Now for confined quark, how the confinement happens. So if you consider the Cork model, we have the different scenario for mesons and baryons. Those are the quarks, are the fundamental or elementary particles which forms these baryons and quarks, sorry, baryons and mesons. So if it's possible to get one quark from this, or is it possible to separate this quark from this particle? So after this Cork model, proposal of this Cork model, many attempts, many efforts were taken to detect a free Cork, but it was explained that the force between the quarks, rapidly becomes stronger, will become very strong as the distance between them increases. So when you try to separate those quarks, for example, in this case, K plus, if you consider, or 5 plus, or anyone, consider this case. This is made up of quark U and S bar, quark up quark and an anti-quark of strange. So if you try to separate these two quarks, when the separation increases, when the distance between them increases, the force between them will become very strong, so that you cannot get separate. You cannot separate them easily. So for force, if you consider, the force between quarks becomes rapidly strong, or it will become very strong as distance between them increases. And this differs from all other kind of forces that we know. And so it needs extremely high energy to release a free quark, or to separate those quark pairs. We need a very strong or very high, extremely high energy. Even if we provide such a huge amount of energy to separate those quarks and make one free quark, it will not be possible. It cannot produce a free quark. Instead, it cannot produce a free quark. Instead, the energy will be used to produce new quark antiquark pair. The new quark antiquark pair will be produced, and the new quark replace the existing quark in the hadron, and releases the released quark combined with the new antiquark to produce a new meson. Okay. So a new meson will be produced. So I will just show it in figure. You can see from here we are considering a proton. It's a baryon. We are considering a proton here. So I have one U here. This is a continuation of that. So this is the Feynman representation of the particles. This is again U. This is D. So this is the representation of a proton in by using the Cork model, and these quarks are interconnected with a very strong force. And if you try to separate these quarks, to separate these quarks, and in order to get a single free quark with some high energy, provide some very high energy, and try to separate these quarks, which forms the proton or any other particle. So if you provide some high energy, theoretically it should we should get a single quark, free quark. But practically it is found that it is not possible. So when you give this much of high energy, suppose the interaction or force between these two quarks will get reduced. This quark and the other two quarks, force between this up quark and other quarks will get reduced. So that we just represented that in here, this particular strand. It shows that the force is getting reduced, and we are expecting that up quark should come out of that particular confinement. Okay. But what actually happens, this will break this high energy, which will break this bonding or the force between interaction between these quarks. So this will break. But this is with presence of high energy. Okay. So when there is very high energy which is present in this particular process, so that high energy will immediately produce a quark antiquark pair. Okay. When this break happens, there is very high energy. That high energy itself is enough to produce this quark antiquark pair. So that antiquark which is produced this antiquark will be this D bar. So because of that high energy, antiquark and quark pair will be produced. So this antiquark D bar will combine with those with that up quark, okay, and the quark which is produced will be combined with the remaining quarks, and this will form a neutron that is nothing but UDD. This neutron is nothing but UDD. We discussed that, which consists of up, down, down quark combination. And this particular one, which will form a meson, which is pi plus. Okay, so basically, if you provide very high energy to this proton, we are expecting release of a free quark, but because of this high energy, what will happen? It will produce one neutron and a meson, which is nothing but pi plus. Okay. So this is a confinement of those quark, because we cannot separate those quark as an individual quark, because when you give very high energy, when this particular interaction breaks, it immediately form a quark antiquark pair. You can see this particular figure, immediately form a quark antiquark pair. So depending upon this quark and antiquark pair, which is just formed because of that high energy, the particles, produced particle will be different. So in this particular case, we are having a down quark and an anti-down quark pair is produced because of that high energy, and that will form a pi plus and a neutron. So it is not possible to separate or to get a free quark by applying very high energy. Instead of that, we will get another pair, which is baryon. So that is the confinement of quarks. And now we will discuss about the colored quark and QCD. QCD is nothing but quantum chromodynamics. Have that separate section. So these are the color quark and quantum chromodynamics. So when you consider the experimental evidence for the quarks, we have Cork's model. You can say that this Cork model, which is just predicted that the baryons are composed of 3 fundamental particles, quarks, and the mesons are having quark antiquark pair, all those things which are predicted by this Cork model, which could explain the SU3 mechanisms, especially unitary transformation mechanisms, and properties of particles. If we are having time, we'll discuss about this. It's not that much important. So it can explain those SU3 mechanisms and the properties of different particles. Okay? And then it could explain the connection between semi-stable particles and their resonances. Resonances we already discussed. So we can, by using the Cork model, we can connect, or we can explain the connection between the semi-stable particles and their resonance particles. And also, by using the Cork model, it could predict, Cork model, it could predict the magnetic moment of various hadrons. It could also predict the result of interaction between different particles. So all this can be done by using or can be predicted by using the Cork model. So first it can explain, the model can explain SU3 mechanism and properties of different particles. Second one is it can connect the semi-stable particles and their resonances, or it can explain the connection between the semi-stable particles and their resonances. And it could also predict the magnetic moment of different hadrons. It could also predict the result of different interaction between. For example, if you consider the experimental scenario, according to the Cork model, the interaction between nucleon and a target composed compared to the pion and same target. So first we consider a nucleon which is interacting with a target, and same with a pion which is also interacting with the target. Nucleon means neutron or proton, and either one of them, and the pion which is also interacting with the same target. Then those interaction will be having 3/2 interaction between nucleon and target compared to pion, and the same target will be having value of 3/2 at high energy. Why? Because at high energy, the probability of interaction is proportional to the number of quarks in the particles. Okay, the probability of interaction is, so what we are considering here. So in this particular scenario, let's consider a neutron. Consider a neutron or a proton which is interacting with a target. Second one is that a pion, let's say pi plus, which is interacting with the same target. Okay. We have neutron and proton, which is interacting with the target. Then we have pion, which is also interacting with the same target. Now, if you consider what is the probability of this interaction, so the probability of interaction should be, if you consider these two, first case this is neutron and proton, which is interacting with the target, and second one is the pion, which is interacting with the target. So the ratio will be, the ratio of those probability will be that 3/2. Why it is? Because at high energy, if you consider at high energy, the probability of interaction is proportional to the number of quarks. The probability of interaction is proportional to number of quarks. So for neutron proton, we have 3 quarks because they are baryons, and for pions, which is meson, which is having only 2 quarks. So at high energy, the interaction is proportional to the number of quarks. So neutron and proton will be having 3 quarks. So the probability of interaction is proportional to 3. And for the pions, we have only 2 quarks. The probability of interaction will be proportional to 2 because at high energy, probability of interaction will be proportional to the number of quarks in that particle. So basically, if you take the interaction probability between this neutron proton and pion, that is the neutron proton, either one of them interacting with the target, to the interaction of pion with the same target, that will be the ratio between these two, that is 3/2. Okay, so this one was experimentally observed that when the interaction, if you consider with neutron or proton with some target, the probability of interaction is 3/2, which means that if you consider that, if you compare that with the interaction of pion with the same target, then you take the ratio between the interaction, then you will get this factor 3/2. So which means that the Cork model is experimentally also it is valid. So by experiment, it is found that the interaction, if you take the interaction of neutron or proton to the target, the ratio between that interaction to the pion interacting with the same target, then you will get 3/2. So this is a prediction by the Cork model, and it was experimentally observed. Another experiment that we can confirm the Cork model experimentally, that experimental number 2. So that is, if you consider the ratio of formation of muon, particles by high energy annihilation from pi minus and p plus. So we are considering the annihilation of pi minus, that is pion and proton p, and pi plus and p. One is pi minus and p, another one is pi plus and p. Both are annihilation process. So which is predicted as 4:1. So by Cork model, if you consider the high energy, the annihilation of pi minus and proton, and annihilation of pi plus and proton, if you take their probability, okay, their formation of, and in that particular annihilation, the formation of muons, okay, muon particles, that ratio, how many number of muons will form in this particular annihilation and in this particular annihilation, that if you predict by using the Cork model, which will be having a factor of 4:1. So in the first annihilation process, we have 4 muons. In the second annihilation process, that is pi plus and proton, we will get 1. Means that the ratio between them will be 4:1, like this, 4:1. Why this is happening? Because since the probability of high energy annihilation is proportional to the sum of squares of the electric charges of the particles and antiparticles. So this particular case, in this particular case, the probability of high energy annihilation is proportional to the sum of squares of the electric charges of the particles and antiparticles. So that is the theoretical concept, theoretical idea by using that Cork model. So if you consider that protons, if you consider proton, which is nothing but UUD, 2 up quark and 1 down quark, okay, like this. And this is interacting with pi plus and pi minus here. Okay. So this will form 1 UD and we have here U bar. Okay. And this particular case, in this particular case, if you consider the charges of this particular reaction, for example, if you consider D down quark, for down quark we have charge which is equal to 1 by 3. For anti down quark, we have minus 1 by 3, just changing that polarity of the charges. And for U, that is up quark, we have 2 by 3 of charge. And for U bar, that is anti up quark, which is minus 2 by 3. Okay, so in the first case, we have UD. This is okay, so this case, we have 1 by 3 plus 1 by 3. Here we have 2 by 3 and 2 by 3, so that is 8 by 9. Okay, so if you consider this case, square of this particles, let's consider this case. This equilibrate is d bar. So if you consider the square of this, so it is 1 by 3 square plus 1 by 3 square. So this will produce 1 by 9 plus 1 by 9. So this is 2 by 9. And if you consider here, it is 2 by 3 square plus 2 by 3 square. So this will produce 4 plus 4 by 9. So it is, if you take the ratio between these two, so that will be 4 is so it should be d bar, right? I think this is this one is ud bar, d bar, and this one is u bar. Okay. So what actually happening? This d is this d changed to d bar here, particular case, and here we have this u bar. So basically, the change happens between these two chords, d to d bar and u to u bar. Okay, so because of that, we have this kind of calculation. So the probability will be proportional to, this is the probability is proportional to the square of the charges. This sum of the squares of the electric charges of the particle. So that is what is happening here. So 1 by 3 for a D, 1 by 3 for D bar. So minus 1 by 3 will comes, but if you take that square, so this is basically minus 1 by 3. So if you take that square, it will become 2 by 9. Similarly, here also we have minus 2, 3 or square. When you take that square, minus will get cancelled. So then we have 8 by 9, and if you take that ratio, then it will become 4:1. So this one also experimentally verified. This ratio also experimentally verified that the proton annihilation, proton in two cases, proton interacting with pi plus and proton interacting with pi minus, and annihilation process happens, and that will produce the meson, and that will produce muon. So this particular muon probability or number of muons that produce in this particular reaction, that is proportional to the sum of the square of the electric charges of particle and antiparticle. And that if you calculate theoretically, you will get 4:1. And if you calculate that probability of formation of muons in these two reactions, then it will also give you 4:1 probability for each of these reactions. So that is also experimentally verified. So these two are the examples which we can have as a confirmation of the Cork model, that the baryons and or the hadrons, which are made up of more fundamental particles, which are called as quarks. Now, as we discussed earlier, if you consider these omega minus particles, which are made up of three strange quarks. So we already discussed which is having 3s for this omega minus particle, and these 3s particles should have a spin up because omega minus is having total of spin 3 by 2. So all these strange quarks should have 3 by 2, and this omega minus is having strangeness of minus 3 because of s is having 1, strangeness quantum number minus 1. So 3s, so minus 3 is the strangeness value. So 3 by 2 is the associated spin. Hence, because of this total spin is 3 by 2, these 3 quarks should have upspin. But it violates the Pauli's exclusion principle, as omega is a fermion with a half integral spin. So if all these having same state, same quantum number, same s, all are having all are same strange quantum number, strange quark, so everything is same. So that is not possible by using by the Pauli's exclusion principle. At least one quantum number should be different. This strange quark or strangeness or anything, something should be changed. Something should change. But in this particular case, and in some other cases also, especially in this case, we have the violation of Pauli's exclusion principle. Hence, another additional quantum number is introduced to solve this problem, and for each quark known as color quantum number. So this color quantum number is introduced, or we can call them as colored quark, which is introduced to tackle this particular problem. So what is this colored quark? So according to this theory, each quark is assigned red, yellow, and blue colors. So there are 3 colors for each quark. One is red, another one is yellow, another one is blue. So each quarks are assigned to have this one of these colors, red, yellow, or blue. And the anti-quarks is assigned to have anti-color, called anti-red, anti-yellow, and anti-blue. So combination, if you consider the combination of 3 colors, combination of 3 different colors, like red, yellow, and blue, if you take the combination of them, then that will produce a colorless situation, colorless quark. Similarly, if you have a red and anti-red pair, a color and it is anti-color pair, then that also produces colorless. Okay. So all hadrons are colorless. Basically, all hadrons are colorless in nature. All hadrons are colorless. Now, if you consider, I will explain that by using this chrome. So that is about the colored quark. I think that is enough because of this violation of Pauli's exclusion principle, we introduce another quantum number or another concept with which is associated with each quark, which is known as the color quantum number. So we introduce another quantum number which is called as color quantum number, or we can say that we introduce another idea which is called as colored quark. So each quark, basically each quarks are associated with a particular color, red, yellow, or blue. And if it is anti-quark, then they are associated with anti-red, anti-yellow. And if you take the combination, three of these colors, then it will become colorless. And if you consider a color and anti-color, then also the particle, the quark will become colorless quark. Okay, and if you consider the hadrons family, all hadrons are colorless. Now, if you look for the quantum chromodynamics, according to quantum chromodynamics, this color is the source of interaction. In quarks, we already discussed that they are very interacting very strongly. They are having very high attractive force between them. And if you try to separate them and to make the free quark, that is not possible. And you have to give very high energy. So according to this QCD, quantum chromodynamics, QCD, so this color is the source of inter-quark force. According to this QCD or quantum chromodynamics, this color is the source of inter-quark force, the force between those quarks. So the force is carried by 8 neutral massless spin 1 particles called as gluons. So the force between these quarks are carried by 8 neutral massless spin 1 particles called as gluons, which are emitted and absorbed by the quarks ceaselessly. We can say this continuously. So these quarks, these gluons, which are emitted and absorbed by those quarks continuously inside those particles. So out of that 8 gluons, there are 8 gluons. 6 of them are color changing gluons, and 2 are color preserving gluons. So out of that 8 gluons, which will act as the colors exchanger between those quarks. Out of these 8 gluons, 6 of them are color changing and 2 are color preserving. So in color changing case, we have the gluon, which is G. We represent them as G, and R B bar. This is a color changing gluon. Or we can have gluon with R Y bar. Then we have gluon with Y B bar, gluon with Y R bar. Then we have gluon with B R bar. B means blue, R means red, Y is yellow, and their anti colors. And the last one, which is gluon with blue and anti-yellow. And these are the 8 color changing gluons, sorry, 6 color changing gluons, and the remaining 2 are color preserving gluons, which are G0. Now let's consider an example. So for example, in this case, you are having an up cork with the blue color. Okay, up cork with the blue color. So what will happen in this case? I just stop that. So for this omega minus case, what will happen? You are having strangeness with the strange cork with the spin up in each cases, so that the Polish exclusion principle is violated here, because we have 3 strange cork like this. They are having spin up, so they are having same energy, same all quantum numbers are same. So it violates Polish exclusion principle. But then we introduce the colored cork concept, so that each individual strange corks will be having different color. For example, this is red, this is yellow, this is blue. So now the quantum number is different. That color quantum number is different, so that the Polish exclusion principle obeyed. Okay, so with the introduction of the colored quark or color quantum number, we can have the Polish exclusion principle validated in this scenario also, with the help of these colored quarks or color quantum numbers. So these particles, even though these particles, these quarks are same, strange quarks, but their color will be different. So the color quantum number will be different. In that way, we can have different difference in quantum number, and the Polish exclusion principle alert, or it is validated. Is valid. So that will not be violated in this particular scenario. So I'm just giving this red, blue, yellow color here. It is not the actual one. So that is the success of this color quantum number. And then if you consider this up cork here, this up cork with the blue color. Now that up cork with the blue color decays into up cork with red color, with the emission of a gluon with a blue and R bar. So this blue is replaced, changed to red, so that we have a gluon with the blue red bar, R bar, that is anti-red. So the newly formed cork is having red colors, that is the anti color which will be as with the gluon. What is the premier color? That is the color which is associated with the cork before decay. That will be the first color associated with the gluon. So gluon will be having this pair. Now this particular example, we'll check another example. So this is a down cork with red color, okay, Dr. So that is interacting with this particular gluon, Dr dash. Okay. Now what will happen? The initial color is red, okay, for this down cork. That is interacting with this particular gluon, which is having color blue and anti-red. So this red and anti-red will combine, and only that blue will remain. So we will have a down cork with blue color. So down cork with red color exchanged or changed to down cork with blue color with the interaction of this particular gluon with the blue and anti-red. Otherwise, you can have a decay like this. The up cork with the blue color decays into up cork with the red color plus a gluon of blue and red anti-red. So this is the basic action which will happen in the decay of these colored corks. Now, finally, we have the standard elementary particles, standard model of the elementary particles. So the elementary particles, we are not considering here the gravitons because gravitons are not yet discovered. So this we are not considering the gravitons here. So the standard model of elementary particles, which we'll be having, the first one is quarks. In quarks, we have up cork, down cork, and then we discussed about strange cork. With this, we have the charm cork, top and bottom. This also we have that we are not going to discuss in this particular lecture. So there are three other corks: charm, top, and bottom. C is for charm, E for top, B for bottom. And then we have lepton family, which are also fundamental or elementary particles. Sorry, which are the elementary particles. Elementary particles means that you cannot divide that particles into any other components. That is the maximum you can go. So we have quarks. In quarks, we have these 6 quarks, and their colored combination on those things are there. And then leptons. In leptons, we have electron, muon, and ton. Electron, muon, ton. And then we have this. There are neutrinos. There are neutrinos also. So these are the elementary particles. You cannot divide electron. You cannot divide muon. You cannot divide ton or any of these particles. So these are the elementary set of particles. So quarks are there. Then we have leptons. Then we have the interaction or the force carriers, or interaction or force carriers. So that includes gluons. This G is for gluon. Gluons, they are the force carriers between those quark pairs. Then we have gamma particles or the photons. Then we have Z bosons. This is Z boson. Yes, Z bosons. Then we have W boson here. This is gamma particles. This is associated with photons. They are the force carriers between those electromagnetic interaction. And this is the Higgs boson. So these are the force carriers. Force carriers or interaction carriers. One is gluon, then is photons, then Z bosons, W bosons, and Higgs bosons. So these are the elementary particles. Standard model of elementary particles. Without those gravitons, we are not including gravitons here. Other than gravitons, these are the elementary particles which we cannot divide again. I think I have told sometime this one, this interaction I have. Example 2. Okay, this is muon. These are not mesons. These are muons. I think I have sometimes mesons, but they are muons. Okay, so they are coming in that lepton family, and they are having this particular quark Okay, so that's all about these particle physics. We'll just consider the same classification here. This picture representing that the standard model of elementary particles. Can have all those quarks here, then we have those leptons here, and we have that force carriers or interaction carriers here. So this is from this set, from this group, these quarks, we have those baryons, hadrons, all those hadron families we have here. Then we have leptons here. We have all those particles, other particles, charge carriers, sorry, force carriers. So in that force carriers itself, this Higgs boson is the scalar boson. These two are gauge bosons, all those things other or vector bosons. So those classification and further classifications also. So just consider this as the standard model of elementary particles. So from this we can have any other particles. We can have any other particles, other atoms, all those things will come from this fundamental or elementary particles. These elementary particles. Okay, so we cannot divide these particles again. Now I will just show you in the previous diagrams we have discussed when we discussed that eightfold way. We discussed about those these particular mesons. So we have Cork and anti-Cork pairs, as you can see, for all those mesons. Okay, so just consider that previous diagram of octet for mesons. Compare with this part in the Cork model. So then we can have this kind of structure or this kind of combination of Cork and anti-Cork. And if you further consider those quarks, we can have different quantum numbers associated with them. And these are the additive quantum number of those quarks. So if you consider electric charge, this is D, U, S. I think this is bottom and top, like that. Then we have electric charge associated with this down quark, up quark. This you can get from your textbook or any other sources. These charts are available, so you just look into that. So this is having minus 1 by 3 of charge, plus 2 by 3 of charge, minus 1 by 3 of charge, plus 2 by 3 of charge, and again minus 1 by 3. You can compare them and classify accordingly and study these properties. Then we have isospin associated with all these quarks. Then we have isospin Z component of the isospin. Then strangeness, charm, bottom, and topness. This is charmness, this is bottomness, this is topness. Okay. For the top particle only we have that topness here. You can see that. For bottom quarks only we have that -1 of quantum number for that particular. That is for bottomness quantum number. But these are the quantum numbers. These are the quantum numbers. And these are the quarks. These are the quarks. For only top quarks, we have +1 of topness quantum number. This one. And for bottom quarks only, we have that -1 bottomness quantum number. Then for +1 quantum number corresponding to that charmness for this charm quark. For all other quarks, we have 0 corresponding to CPT. And only for those quarks, we have that charmness, bottomness, and topness. So this chart you will get from online itself. You can look into that and study. Also, you can see from here this set. the set of values, consider these values are 0 for charm bottom and top quarks. For those quarks, we do not have any isospin. Z component of isospin is 0, isospin is 0, strangeness is 0. We consider this set is also 0 for those DUS, that is down, up, and strange quarks, because they do not have any charmness, they do not have any bottomness, topness that is associated with this charm bottom and top quarks only. This is minus. Okay. Also, I will just show you one other. Okay, so that's all about the particle physics. Okay, so that's about the Cork model. The end of